Benvenuto al webinar. Ci si è collegati con il ruolo di partecipante in grado solo di ascoltare.
Moltissimo in funzione anche di quella che è la combinazione, la mutua combinazione della tipologia di radici di apparato radicale che si va a innestare in una configurazione di grani che può essere la più varia possibile. Quindi questa è una schematizzazione che mostra quello che è l'effetto delle radici su diverse configurazioni iniziali di grani. E tra l'altro queste osservazioni possono essere fatte se appunto si ha la possibilità di poter effettuare anche una sperimentazione delle osservazioni alla microscala, come questa che vi mostro. Questa è una figura estratta da un lavoro del collega Alessandro Gracica in Ispra, con il quale sto collaborando su questo tema di ricerca. E dicevo, il contributo e l'effetto della presenza delle radici sulla porosità poi si traduce anche su quelle che sono le proprietà di ritenzione del terreno. Qui vediamo la rappresentazione di alcune curve di ritenzione per diversi terreni che mostrano, in alcuni casi come in questi, mostrano l'effetto della vegetazione nell'andare a ridurre quelle che sono le proprietà di ritenzione, ma ci sono altri esempi appunto derivanti da risultanze sperimentali sia di sito che di laboratorio che mostrano invece un incremento delle proprietà ritentive quando il terreno quando appunto si va a considerare il contributo delle radici. Quindi il quadro il quadro che abbiamo ad oggi per quelle che sono le evidenze sperimentali ad oggi ancora è un quadro che deve essere ancora chiarito, o meglio non ci sono probabilmente indicazioni univoche proprio per il fatto che il particolare terreno va a combinarsi con quell'apparato radicale specifico e ciò può dare luogo a scenari diversi. Anche in termini poi di conducibilità, questo aspetto si traduce anche in termini di variazione della conducibilità idraulica. Ancora questo è un diagramma che mostra il coefficiente di permeabilità in funzione dell'indice dei vuoti e generalmente mostra un incremento di permeabilità del terreno radicato rispetto al terreno non radicato, non vegetato, ad eccezione di situazioni in cui l'indice dei vuoti è molto basso, per cui questo effetto è minore. Ora, questo cappello, ce l'ho ancora 3 minuti? Ok, velocissimo allora. Un caso studio in corso, trattato ad oggi, studiato ad oggi, secondo quello che è il primo livello di complessità, come dire, che ho delineato, cioè quello in cui si considera il rinforzo meccanico e qualche osservazione sulla porosità derivante da misure in situ consentirà poi di poter auspicabilmente arrivare a un livello di complessità 2 di trattazione del problema in cui si considerano i processi idromeccanici. Allora, siamo in provincia, nel comune di Norcia, regione Umbria. Questa che vedete è l'estensione di un fenomeno di debris flow, in realtà 2 fenomeni che si sono verificati nel 2012 e 2015, successivi a fenomeni di taglio, quindi di deforestazione, di taglio di alberi e dunque apparati radicali, che hanno interessato queste aree che vedete qui perimetrate nel rosso. Si tratta la vegetazione costituita da faggi, caratterizzati da radici molto sottili di quest'ordine di grandezza, e questo che vedete sulla vostra destra è l'andamento del profilo radicale con la vegetazione, appunto che interessa prevalentemente il topsoil, quindi i primi 50 cm di profondità. Abbiamo caratterizzato le radici, abbiamo caratterizzato alcune delle proprietà fisico-meccaniche terrene a livello molto basico, vorrei dire, attraverso prove assolutamente convenzionali di taglio diretto, come potete vedere in queste immagini. Abbiamo fatto qualche misura di ritenzione in sito e in laboratorio e abbiamo fatto qualche misura di resistenza in sito attraverso un'apparecchiatura, anche qui direi veramente molto molto semplice. Di fatto è un'attrezzatura che prende il nome di corkscrew test e che permette di misurare una resistenza allo sfilamento del terreno radicato e poter quindi poi, per in corrispondenza della porzione più superficiale di pendio, andare poi a poter calcolare l'incremento di resistenza dovuto alla vegetazione. E cosa abbiamo osservato? Naturalmente questi sono veramente i primissimi risultati. Quello che abbiamo osservato è che intanto nella zona, come dire, soggetta al taglio di vegetazione, abbiamo dei valori di resistenza al taglio del terreno inferiori a quelli che invece sono stati ottenuti nella zona appunto non soggetta al taglio di vegetazione. Quindi qui il target, l'obiettivo del lavoro è quello di andare a considerare non tanto l'effetto della presenza di vegetazione, ma quanto l'effetto invece sfavorevole che porta il taglio della vegetazione. E siamo stati in grado anche, attraverso queste misure semplicissime, di andare a poter calibrare, siamo stati in grado di poter calibrare quel coefficiente K secondo di cui vi parlavo poco fa, che appunto a volte cautelativamente viene assegnato un valore di tentativo, ma in questo modo, attraverso questo approccio integrato di misure in sito e misure di laboratorio, abbiamo potuto calibrare correttamente. Vado alle conclusioni, una slide di conclusioni me lo concedi. Allora, sicuramente c'è moltissimo da fare ancora, da studiare, da comprendere in primo luogo, per poter tener conto della variabilità delle proprietà fisico-meccaniche dei terreni radicati, che è una variabilità spaziale e temporale che deve essere considerata nei modelli. Le piante, cosa che ho imparato, ecco, anche attraverso le utili discussioni che abbiamo avuto nel corso del convegno Roots 25 a Bari, sentendo colleghi esperti anche di altri settori, le piante sono degli organismi sociali, sofisticati, evoluti, quindi hanno una variabilità interna che deriva anche dal loro adattamento ambientale, quindi sono delle vere e proprie comunità che interagiscono con il terreno, bisogna tenerne conto. Forse ciò porta a pensare che l'approccio ingegneristico nel considerare le radici come fibre naturali, proprio per tener conto in ragione della variabilità delle proprietà biomeccaniche, può risultare semplicistico. E quindi questo è il motivo per cui l'approccio semplificato nel considerare il rinforzo meccanico semplicemente rinforzo meccanico è un approccio riduttivo, motivo per cui dobbiamo tendere e quindi sviluppare la ricerca perché si possa addivenire secondo l'approccio appunto che vede una combinazione di problemi come chiaramente indicati dalla professoressa Cotecchia. L'ultima cosa che vorrei dire è che ad oggi forse non abbiamo ancora dei protocolli sperimentali, delle procedure sperimentali, come dire, regolate, regolamentate, che ci permettano poi di portare avanti una sperimentazione che possa essere condivisa anche da tutti i ricercatori che lavorano sul tema. Quindi secondo me uno sforzo in tal senso, voglio dire, è auspicabile. Non dico nulla su Roots, mi piace solamente chiudere con un'immagine, semplicemente un'immagine che mostra alcuni interventi di sistemazione di versanti. Siamo in Val Gardena, qui vicino, una zona che io frequento durante le vacanze, e a testimonianza di come le nature-based solution siano assolutamente ad oggi anche largamente impiegate, e come in questo territorio mi sento di poter dire, da quello che vedo semplicemente da un anno a un altro, c'è un'attenzione veramente e una cura veramente importante che si osserva appunto nel, tra l'altro, progettare e realizzare opere in tempi molto rapidi, opere che si adattano perfettamente, allineano perfettamente con quello che è il contesto montano. Quindi grazie a tutti voi.
Va bene. Allora, intanto grazie, un bellissimo intervento. Aspetta, ti do il dono dell'ordine degli ingegneri della provincia autonoma di Bolzano. Volevo dire che adesso ci sarebbe l'intervallo, però prima dell'intervallo potremmo dedicare 5 minuti a eventuali domande da casa, cioè da remoto, oppure qui in sala, alle 2 relazioni che abbiamo sentito questa mattina, così le facciamo a caldo e non ci si dimentica degli argomenti esposti. Quindi se c'è qualcuno che vuole fare delle domande, Fabio, se c'è, non so come funziona per chi è collegato da remoto. So che ci sta vedendo, ci sta ascoltando anche il professore Versa, ex presidente Aggi, affezionato anche lui a Bolzano, e quindi porto i suoi saluti. Dalla sala non vedo mani alzate, vogliono tutti il caffè. Da remoto?
Non mi sembra.
Hanno
alzato il dito, vuol dire che vogliono il caffè.
Vogliono il caffè anche loro. Allora ce n'è uno di Daniele. Prego Daniele.
Abbiamo anche il microfono.
Vieni qua.
No, più che una domanda è una considerazione. Secondo me, rispetto all'inizio di quando si cominciava 25, 30, 40 anni fa a trattare l'argomento, mi sembra molto importante sottolineare l'aspetto delle proprietà biomeccaniche. Parlavo anche col direttore Günther durante l'intervento di Manuela, tenere presente la situazione evolutiva delle piante. Tu hai fatto vedere una slide in cui c'era questa pianta e poi dopo quasi morta. Qui in Trentino, in Alto Adige, c'è molto il problema, e anche nel Bellunese, della malattia del bostrico, che ha condizionato pesantemente gli ultimi anni, anche in funzione delle evoluzioni climatiche del territorio. Quindi è un'ulteriore variabile da aggiungere, ma quanto mai auspicabile. Non so se volete commentare, ma mi sembra fondamentale questo aspetto.
Mezz'ora.
No, ma hai detto tutto tu, non c'è molto da commentare, nel senso questo anche dell'aggressione da parte di questi parassiti è un altro aspetto importante da dover considerare. Ecco, appunto, comprendere dapprima quelli che sono i meccanismi e poter tener conto di questa variabilità dello stato di salute della pianta, sia la parte epigea, qualunque pianta sia l'apparato radicale in profondità, perché poi questa determina, cioè quelle grandezze che concorrono all'incremento di resistenza al taglio sono queste quindi che derivano, e quindi è assolutamente necessario. Credo che non se ne possa fare a meno di fare calcoli appunto più semplici, più semplicistici, però rischiare poi forse di andare a sovrastimare il contributo. Questo è un po' a mio avviso il rischio, evidentemente.
È una domanda veramente
puntuale.
Sì, puntuale, cioè mi inserisco proprio in sequenza, perché su questo discorso della variabilità delle caratteristiche delle radici in funzione dello sviluppo della pianta e di ciò che può accadere, no? Quindi il bostrico successivo alla tempesta baia. Quindi la professoressa Cecconi ci ha fatto vedere un test veloce, Skew Cork test, ripeto giusto? Cork Skew. Quindi approfitto della presenza del direttore Günther, il servizio forestale, quindi che sorveglia appunto le foreste nel nostro territorio, fa sicuramente test sulle piante, le vedo fare nella nostra sede del Dipartimento a Trento, no? le test sui tronchi. Quindi se esistono test che sembrano relativamente speditivi, ovviamente ci vuole competenza poi per l'interpretazione, da poter fare sul terreno vegetato. C'è un'usanza nell'ambito forestale di fare dei test anche sul suolo vegetato, o può essere appunto inserito, questa usanza può essere inserita in collaborazione con i geotecnici, gli ingegneri geotecnici?
Grazie per questa domanda. No, chiaramente ci sono dei test e subito, anche dopo l'evento VAIA, c'è stata una diretta poi collaborazione anche con l'Università di Bolzano per vedere di quanto poi si modifica anche il deflusso su queste aree colpite prima dalla tempesta, ma adesso poi successivamente anche da altri eventi. Abbiamo avuto poi schianti da neve e successivamente poi anche il bostrico, di quanto poi su delle superfici abbastanza poi vaste colpite, di come cambia poi l'aspetto idrogeologico. Questo per noi chiaramente è molto fondamentale. Siamo sempre stati dell'opinione che con la martellata, vuol dire con la valutazione del forestale prima che una pianta poteva essere tagliata, si considerava anche questo aspetto idrogeologico, che effetto avrà se togliamo delle piante da da un versante. Adesso con questi eventi straordinari, diciamo, si è un po' capovolta la situazione, non è stata più una scelta mirata del forestale, ma è stata una scelta voluta da qualcuno che ci sta sopra, e questo ha fatto sì che bisogna anche un po' rivalutare, rivedere di come si comportino questi sistemi, diciamo, no? Sinceramente non siamo stati abituati a dei fenomeni di questo tipo, perché fino al 2018 la nostra situazione era abbastanza tranquilla, magari qualcosa di piccolo sì, ma non di queste ampiezze, e purtroppo siamo anche consci che non è la fine, è sicuramente l'inizio di un periodo molto, molto movimentato, e per questo motivo assolutamente questi studi sono di grandissima importanza.
Giusto un brevissimo commento in aggiunta, che sì, in effetti tutti questi eventi che definiamo straordinari in realtà sono relativamente poco straordinari adesso, perché noi ad esempio dalla Puglia abbiamo la questione della xylella, che ormai da anni diciamo un po' ci ha creato un po' di problemi, soprattutto all'ulivo. Certo, spesso questo non ha avuto poi impatti su altre tipologie di fenomeni, quali quelli ad esempio dell'instabilità dei pendii, però diciamo queste cose stanno succedendo sempre più spesso, e quindi forse diciamo nel lungo termine li includeremo come problemi ordinari nella progettazione di questi interventi. Noi poi tra l'altro, io forse farò un brevissimo cenno quando oggi pomeriggio parlerò, abbiamo anche avuto sul campo prove che abbiamo fatto sul pendio di Pisciolo 2 incendi che hanno chiaramente dato problemi a noi che stavamo monitorando lo stato del terreno, ma chiaramente anche alla vegetazione che avevamo installato, quindi diciamo questo poi a ulteriore argomento. E poi un'ultimissima cosa, questione biologica, cioè secondo noi ne parliamo spesso, sta diventando sempre più importante. Giusto per dare un cenno, l'attività scientifica di frontiera adesso sta addirittura studiando, da qualche anno ormai noi non siamo coinvolti, l'utilizzo di alcuni funghi specifici che sono in grado di ulteriormente incrementare o addirittura inibire la crescita, ad esempio, dell'apparato radicale. Allora, chiaramente queste non sono cose che magari riusciremo a implementare nell'arco di pochi anni, ma magari nel medio termine saremo in grado di ingegnerizzare la crescita e lo stato della pianta per far sì che possa essere utile, diciamo, per gli scopi che magari si...
non è che volevo fare una considerazione, no? Innanzitutto penso che quell'intervento che ha fatto vedere la professoressa in Val Gardena è uno degli interventi, diciamo che da noi la parola era ingegneria naturalistica ancora adesso, no? È nata già 30-40 anni fa anche con il professor Florinet, che recentemente è scomparso e ha lavorato per anni alla Pacini Montani, poi è diventato professore a Vienna alla BOCU. No? Quindi il ruolo della vegetazione e dell'effetto delle radici diciamo, è stato studiato magari non così ingegneristicamente come viene adesso studiato. Noi come Bacini Montani abbiamo dei vivai, nei quali insieme alla forestale curiamo due vivai, uno in quota più bassa e uno in Valle alla Orina, insieme alla forestale, in cui ci facciamo crescere le piante che poi ci servono per fare questi lavori in questa zona. Però discutevo anche con Luca, che è molto importante secondo me. A volte affrontiamo, diciamo, il nostro metodo di lavoro è un po', devo dire, trial and error, no? La Bacini Montani storicamente, diciamo così, ha sempre operato, diciamo, facendo anche delle prove, no? Senza troppa ingegneria, diciamo così, senza troppi calcoli, no? Però per certi tipi di problemi, secondo me, dove vedi che la frana non si ferma da 10-15 anni perché tu la tappezzi di qua, la tappezzi di là, no? Forse conviene un attimo fermarsi, un po' la metodologia, dare un incarico all'università e studiamo 5 anni, vabbè, però poi dopo possiamo magari, discutevo con Victor, anche trovare un modello che ci permette poi di sistemare questa frana in modo quasi definitivo, no? Ovviamente non possiamo farlo per tutto il territorio, a volte, come ho detto, siamo veloci, reagiamo e cerchiamo di stabilizzare queste frane superficiali, no? Mi ricordo nell'anno 2000 c'era il poligono di tiro dei militari, lì era superoso e noi siamo intervenuti con rinaturalizzazioni e ha funzionato, no? Quindi voglio dire che il lavoro ce n'è, è molto interessante questo argomento. Prego.
No, giusto una curiosità, parlando dell'argomento sull'effetto di rinforzo, no, della vegetazione sulla stabilità degli individui. Secondo me è un aspetto forse non troppo sviluppato in questo momento, che però per me rappresenta una chiave fondamentale anche per implementare modelli avanzati in genere su questo tipo di analisi, che è quella dell'elemento rappresentativo di volume, no? Dal punto di vista sperimentale, tutti questi parametri che vanno messi dentro queste analisi, avendo a che fare con delle radici, quindi un mondo molto eterogeneo, andrebbero probabilmente determinati ad essere poi scalati, no? All'applicazione sull'elemento rappresentativo. Quindi io mi domando, ci sono degli studi, perché io mi ero interessato per un certo periodo, adesso ho smesso da qualche anno, vorrei ricominciare, che prendono in considerazione l'effetto scala proprio sperimentale della determinazione di tutti i parametri, sia idraulici che meccanici, connessi agli effetti delle radici. Perché secondo me la tecnica di laboratorio più appropriata è quella che deve darmi poi parametri di progetto, che devo mettere nei modelli sia disaccoppiati che anche nei modelli più semplici, dei microlimiti, diciamo, un'analisi più semplice e universale. Quindi su questo volevo sapere a che punto.
Sicuramente degli studi che appunto evidenziano, ci sono degli studi che evidenziano come la questione appunto della scala dell'analisi e quindi del volume rappresentativo e quindi sia da considerare e studi che indicano e suggeriscono quelle che in funzione della scala di osservazione e di indagine evidentemente sono poi i parametri che devono essere determinati poi sperimentalmente. Il problema è che c'è poi una difficoltà che secondo me appunto sulla quale bisogna lavorare dal punto di vista della ricerca scientifica, è quella di portare avanti una sperimentazione, dicevo anche di complessità, no? Crescente, che si adegui poi alla scala di indagine, che sia adeguata per la scala di indagine, di osservazione e di analisi. E secondo me ad oggi ci sono tanti studi con indicazioni diverse, impiego di apparecchiature anche molto sofisticate, di strumentazione molto sofisticata, però probabilmente ancora occorrerebbe lavorare per dare delle indicazioni che possono essere poi di utilità un po' per tutti. Ci sono anche diversi studi, non solo singoli, ma come dire delle review di letteratura, al quale molti colleghi di noi hanno anche lavorato e partecipato, che consentono appunto portano in rassegna tutto quello che è stato fatto in materia e quindi sono utili per uno sviluppo ulteriore. Io penso che ad oggi, almeno è quella che un po' sento come esigenza, credo che sia importante poter dare qualche indicazione in più a chi si occupa di ricerca sperimentale, laboratorio di sito, per poter condividere alcune scelte nella scelta delle apparecchiature, nella scelta delle scale. Non so, il solo problema della dimensione del campione di laboratorio su cui fare una prova. Che questo è un problema da capire. È difficile chiaramente perché è tutto, abbiamo detto che dipende fortemente dalla combinazione di quel particolare terreno. Ok. E quella particolare specie erbacea, quella particolare apparato radicale, quindi è molto complesso la problematica. Per questo come gruppo di ricerca ci stiamo muovendo, cercando di individuare appunto livelli, quello che dicevamo, livelli di complessità crescenti per poter portare avanti diciamo, uno studio sistematico che porti da prima a evidenziare i problemi, comprenderli e poi poterli trattare. Credo. Grazie a tutti.
No, volevo solo contribuire a questa valutazione, quello che ha detto Manuela, diciamo, sia per la parte meccanica ma anche per la parte idraulica. Nel contesto di RUTS si discute molto di prove in sito, cioè di test in sito, quindi monitoraggio in sito anche con controllo dello stato vegetativo verso il laboratorio e modelli fisici. Io sono una fautrice del sito perché non c'è niente da fare, il clima e questa interazione per come si sviluppa il sito non è necessariamente così fedelmente riproducibile in laboratorio, anche nei modelli di relazioni fisiche. Certo, per il dettaglio ti serve il laboratorio e ti serve il modello fisico, per alcuni aspetti di dettaglio, ma diciamo, però questi test, questi field test sono onerosissimi, non c'è l'incendio, non c'è l'aggressione degli animali, quindi diciamo è una ricerca molto costosa, ecco, lenta in questo senso.
Allora ringrazio tutti per le domande e per la discussione e noi adesso abbiamo il coffee break, siamo in ritardo con una precisione cronometrica di mezz'ora e quindi però ci sono dei tempi larghi, quindi va bene tutto. Vi chiederei di ridurre l'intervallo, il coffee break a 20 minuti, quindi ci vediamo qui in sala alle 11:50. Grazie.
Can I copy my slides? So I'm presenting next. Can I copy my slides? Ja, ja. Also, ich habe meine Folien hier, aber ich habe keine Flash-Drive oder
Vielleicht
USB.
kann man das, ich weiß nicht,
Clicca qui, clicca
Sì,
qui.
no, ma non mi fa vedere. Aspetta.
No, qua, devi cliccare qua.
No, dovrebbe venire un'altra
Vai.
finestra. Non
È così,
giusto,
è questo.
no. Sono sicuro perché...
Ah, perché ti fa... Aspetta, ritorni indietro.
Aspetta. Ok.
Ci sei?
Vedrai che adesso... Condividi.
Se provi uno di questi. L'altro. Ecco. Non è questo.
Ok. Dobbiamo un attimo, penso, aspettare Sabrina che deve aprire il collegamento con l'esterno. Wait, eine Sekunde. Sì. Vediamo se... Vedi che non è...
Non è facile.
Ja. Warte. Ich muss das Condividi. Ich verstehe das nicht. Wieso?
Also wir sind
Jetzt.
Ja.
Okay. Jetzt passt das.
Perfetto.
Okay. Warte, ich sage dir Bescheid, wenn du beginnen kannst.
Ja.
Warte.
Ah, no? Sì. Se no vai.
No, ma
Possiamo iniziare? Allora, ci siamo, iniziamo la seconda parte della seduta, della sessione mattutina. Il prossimo intervento è del dottore Ildiz della Università di Aachen, che ci parlerà del Pilot Memo, un open source research software for unifying root reinforcement models. 30 minuti a partire da adesso, prego, e grazie.
Grazie mille. Buongiorno a tutti. Hallo zusammen. Unfortunately, I don't have enough Italian to give this talk in Italian. That's why it is going to be in English. If you have any questions during the talk, you can also just interrupt and then I will try to explain. So I'm going to present a software that we published together with my colleague Gerrit Meijer from University of Bath in the United Kingdom on integrating root reinforcement models to predict the mechanical reinforcement using various models available in the literature. And and I've always been intrigued by the question, why does a slope fail but not the next one? Why does an area fail but not the next one? And why does it happen this year but not last year, right? And in order to answer this question, we need to look at two things, right? The first one is the reason why, so we need to look at the mechanisms. And we also need to define a question. We need to answer the question, how can we define the susceptibility to mostly rainfall triggered failure? So that's my main interest, the shallow landslides that are mainly occurring after a heavy rainfall event. So nothing to do with the seismicity and etc. And the research in this topic actually is not very old. It started end of 60s and in 70s. And I looked into why did it start? How did it start in that time, right? And there's one specific problem that especially characterizes the post-war era in United States. There was an increased demand in housing. And the United States Department of Agriculture, USDA Forest Service, in 1958 made a declaration that there is an increased need for timber. And afterwards, there was timber harvesting everywhere in US, which resulted in clear cutting in many areas. I mean, we know quite well if we take the forest down, also the mountain will come down, right? And then people observed this in the subsequent years after this effort in removing many of the forested areas for timber harvesting. And of course, then a public opposition started, especially in 1960s and 70s, which is also called as the environmentalism and public participation era. And afterwards, the Senate started investigating this, right? So they called professors such as Donald Gray, which is a big name in US in the 1960s, Lawrence Waldron, and Professor Wu, and etc. And they started looking into trying to understand the mechanisms why deforestation, why clear cutting ends up in landslides and debris flows and increased erosions. And that is how all the research started back then. Of course, the first evidences were anecdotal, and then it was experimental, and then there were efforts to turn this into models. And after understanding why deforestation ends up with landslides, we started thinking about the second problem, right? If we define areas that are susceptible to failure, what can we do to prevent failures? And we don't want to bury lots of concrete in nice areas, in forests and in mountains. And we turned into what is called a soil bioengineering solution, so hybrid solutions, one can also call it, right? But these are mostly experience and observation based, right? We know plants help, so we go and plant willows there, we go and plant lolium there, and then we say, okay, this stock is now stable. There's hardly any engineering calculation involved. But we know there are models available that we can utilize at different scales with all the problems of lab testing and field testing and etc., but they are actually applicable models. Now let's have a quick look how do actually plants affect slope stability. I mean, the first two talks from Professor Kotecha and Professor Cecconi did a great introduction, so I'll pass this part rather quick. So we know they have two fundamental effects. There is the hydrological effect and mechanical effect. And we cannot really separate these effects from each other, right? Because we know vegetation does one thing, it removes water, so it reduces the water content of the soil. This in turn applies a matrix suction. It increases the suction, which increases the strength. But then we also have a direct mechanical contribution via roots. If there are roots crossing through a shear surface, then we will have an increase in that area, increase in strength in that area. But we also have negative effects. There are not only positive effects, right? And it always starts with a rainfall. And the first positive effect we can talk about is interception. So when there's rainfall, when there's rainfall, the canopy interception reduces the water that is reaching to the soil. And it all becomes water management problems in shallow landscapes, right? And we are trying to manage the water. But once the rainfall reaches the soil and infiltration starts, we have transpiration. So roots, via root water uptake, gets water from the soil and lets it out from their above ground biomass, right? And we also combine this with evaporation because we also have soil, so the soil is evaporating from there. And this term is named as evapotranspiration, so combined loss of water via evaporation and transpiration by roots. And on the negative side, the roots create preferential flow paths. So not only the roots, also the tree trunks. So you may see in heavy rainfall, water directly flowing along the tree trunk and then reaching to the soil directly under the canopy, and where you have thick roots that created these preferential flow paths, right? So this will in turn be a negative effect that would reduce your suctions in soil. Then we have the mechanical effect. So if we have roots crossing through a shear surface, we have the tensile stress developing on the roots, and that provides a mechanical contribution. So as an engineering material, it's not different than, let's say, cables. So they work in tension, but of course they also have bending. They can work in bending as well. Then an effect that is largely ignored is actually also Professor Cecconi showed this, the formation of stable aggregates. So the whole pore size distribution changes with the presence of roots and other soil fauna, such as the mycorrhizal fungi and other microorganisms in the soil. Then we have effects of the wind from trees, so they can uplift, and then they can cause problems, and they can reduce, so they can actually trigger landslides as well if you have large trees. And they also had a surcharge, but it is not a very, very critical effect, I would say. So all in all, the rest of the talk will be on the mechanical reinforcement, right? We are going to look into the models that were also introduced earlier, and then look at our solutions. So if you look at models at an individual root scale, we always start from that, right? So we have a three-dimensional root segment that is embedded in soil, and the soil starts displacing. So we can simply think of this as the slope starting moving down. And we have elongation on the root, and this elongation then applies a tensile stress, so the tensile stress develops in the root. So this is the fundamental mechanism for all the models that we are going to see in the upcoming slides. So one of the early examples is Waldron 1977 model. So there are 4 components in this model. The first one is soil shear displacement. So when the slope starts moving, it creates root pull-out displacement. So the roots start elongating. And this elongation then starts developing a pull-out force. And this root pull-out forces turns into a soil reinforcement. And if we combine all effects of roots, then we end up with this value that is denoted as root cohesion, which is the strength increase. But the roots behave differently with increasing load. We can either have roots that are breaking, or we can have roots that are slipping. So if you think of an anchored system, an anchored cable or so, this can either break, so the cable can either break, or the cable or the whole anchor system can come out from the embedded area. And this is the same for the roots. Some roots break, some roots slip out. And this is controlled via the interface strength between the soil and roots. But what do we need to implement the Waldron 77 model? I mean, it's so easy to go through these models because they're mostly like limit equilibrium based and force balance based and etc. They're not complicated models, right? And we need some parameters such as soil properties, friction angle, and failure plane properties. So we need root properties, diameter, tensile strength, and stiffness. We need shear zone properties, cross-sectional area and shear zone thickness. We need root soil interface properties, interface strength, and we need some, well, we don't really need, but we have some optional root properties, such as the anchored length, if we account for root slippage, or initial root orientation, if you want to do 2D, 3D root orientations. Now, if you go to the next family, the Wu-Waldron type models. So in the Waldron model, we are considering the mobilization of the tensile stress, but in the Wu-Waldron type model, there is no mobilization. Okay, and we also assume that all roots break at the same time. So obviously, it's not a very realistic model, but it is used a lot. Why? Because it's a very simple model. You require only 3 parameters. You need root diameter, tensile strength of the roots, and you need the cross-section. That's it. And then you have your number, you have your root cohesion number, and we will see later how variable this root cohesion value is. Then the next scale from individual root to the next scale will be the root bundle scale, right? And there's this general family of fiber bundle models also introduced earlier. So instead of considering individual roots, we now look at bundles of roots, and we now look at how they fail during elongation and how we redistribute the load if one root fails. Okay, so we consider a bundle of roots, and we let them fail individually. They can also slip out, by the way. And we have this load distribution factor. If it is 0, that means each intact root must carry the same tensile force. If it is 2, that means each intact root must carry the same tensile stress. And this is an assumption. And there are many, many experimental work that fit fiber bundle models and come up with these beta values. And what is the main difference between a Wu-Waldron type model between the fiber bundle model? So if we look at the Wu-Waldron type, we have the effects of individual roots. There's no mobilization due to soil displacement. We have a peak reinforcement that is occurring in the end, and then we have failure afterwards because all roots break simultaneously. And if you look at the sequential failures, this can either be in the Waldron type, it can also be in the fiber bundle model family. We have an increase due to this combination of roots, and some roots fail because they reach to their tensile strength. And then we have different levels of reinforcement, and we try to identify what is the peak reinforcement. In this example, the peak reinforcement occurs in the beginning, but this is not always the case. Due to the combination of different diameters and species, it can also happen in the later stages. It does not need to be reaching to peak and then reducing. Now let's look at what do we need for fiber bundle model. So we need diameter, tensile strength, and we need the cross-sectional area, very similar to Boolder model, and then we need this load sharing parameter, which is the beta that I mentioned earlier. So we have these models. There are many, many others available in the literature. There are many derivations of fiber bundle, root bundle models available. And there are also many analytical models. But we decided that we need a platform actually to work with these models. And the reason is the following. At different scales, from individual root to root bundle and to slope scale, we have many models available which use different parameters, which have different assumptions. And the question we want to answer is, how can we easily compare different model predictions, and how can we select actually the right model for the problem that I'm working on? And then we look at the terminology, because this field comprises of geotechnical engineers, but there are also many people from different backgrounds, and then sometimes we refer to the same concept with different names. And the models also use different parameters, or sometimes the models use the same parameter, but they name it differently. So we also wanted to introduce a controlled terminology, a controlled vocabulary. Then that's why we define soil strength, root geometry parameters, biomechanical properties, root quantities, and soil root interface. And the question we are interested in here is, how can we ensure that we are talking about the same thing when we refer to a parameter? Then lastly, some models were developed in states using imperial units. Some models in Europe using SI units. Parameters were introduced that had no dimensions. Parameters that were introduced that had dimensions of quite random units, because it was just a statistical parameter to do a fitting. And then, of course, we end up with many different combinations of units. So we also needed to introduce a system that we can consistently avoid errors, and we don't need to convert every time when we have different parameters, right? And my colleague Garrett Mayer, during the Soil Bioengineering Conference in 2025 in Mexico, he did a survey there. And one question in the survey during this conference was, what do you prioritize when choosing a root cohesion model? So there are two answers that has the highest number, right? One is reliability of predictions. That is actually great. So we still value the reliability of what we are coming up with the numbers with our models. But the other two is simplicity of calculations, small number of input parameters, and then the third one coming after it is availability of code or software. And then we thought, okay, why don't we come up with a software platform that we provide simple calculations for these models, that we control the parameters and the vocabulary, that we also make this publicly available in an open source way. That's why we develop PyRoot Memo. So it's an open source Python package for root reinforcement predictions, which relies on object-oriented programming, which unifies model terminology. It streamlines the use of units. It facilitates quick and transparent model selection, calculations, and comparisons. You can also do additional tasks such as sensitivity analysis and uncertainty quantification using this package. So what do we do with that, right? So in the object-oriented approach, we have classes, and from these classes, we create objects. So classes has attributes and methods. Attributes are basically data, and methods are functions. So we create a sand object, we create a clay object, we create a root object, and etc. And how is the package structured? So we have a materials module, we have a models module, we have a geometry module, and we have utilities. And in the materials, we have roots, soil, and interface classes. And in order to provide this controlled vocabulary, we have some global parameter listings that we introduced. This also helped us to control what the users can enter. So it's completely error prone, and we don't let users to enter non-physical values and etc. And afterwards, let's look at how we actually build models from the objects. So we have the roots, we have the failure surface, interface, soil profile, and we have soil. then if we look at the models that we have implemented so far, we have Wu and Waldron, fiber bundle, root bundle, Waldron model, and drum. Each has different requirements. For example, for Wu and Waldron, you need roots and failure surface information. For drum, you need roots and failure surface, as well as interface and soil profile information. Afterwards, it becomes as simple as creating objects. So we have, for example, an object we called as roots. So this is consisting of multiple roots of Alnus incana that has different diameters, and it has measured or estimated tensile strength values. It has also elastic modulus that are shared for the roots, and it also has length values. Afterwards, we create a soil type, a soil object. Then we create a soil profile of 500 millimeters of using one soil type. We define our interface strength that are coming from the experiments, and then we define our cross-sectional area and the depth of the shear plane and the shear zone thickness. Now, let's look at how simple it is actually to calculate the root reinforcement with this software. Once we create all the objects that we need for the models, if we want to calculate the fiber bundle model, for example, the reinforcement from fiber bundle model, we just need to call the fiber bundle model class here, and then we pass the roots object, and then we define the load sharing value. We can also test different assumptions of load sharing value and see their effects. So for example, if you assume the load sharing value is 0, or if you assume load sharing value is 2, you can directly see what is the total force on the roots. Or you can test different fiber bundle families. So for example, the root bundle model with the Weibull survival function, and you can see here the comparison between these models. You can also test different mechanical assumptions. So for example, if you use the Waldron model, and if you assume roots break and slip, or roots break only, we can see the effects of this, and we can get the reinforcement immediately. And once we create this model objects, all we need to do is to call the peak reinforcement value from the model, and then you end up with this root cohesion value. So I have one more example of what we can do with the with this package, because it's something that I considered quite important, and I'm going to very quickly mention this application as well. So we have these models, we predicted a value, and we want to have a reliability in our value, right? And we know our system is complex and there are many uncertain input parameters. What we can do is we can estimate the uncertainty of our root cohesion value, our peak reinforcement value. But what is important is to understand how this uncertainty propagated through our model, and how we can reduce this uncertainty. And in order to reduce this uncertainty, we need to understand the sensitivity of the model parameters to the output. So we need to conduct what is called as a global sensitivity analysis, and we need to target which are the parameters that we can eliminate from the model, or which are the parameters that creates the most uncertainty. What can we do with this? If we know root diameter is the most crucial parameter in determining my uncertainty, I can invest more effort in better measurements of root diameter so that I can reduce the error. Or if I see that the elastic modulus doesn't really play much role, even though it's one of the parameters, I don't need to maybe worry too much about getting very accurate elastic modulus values, but I can go with literature values. So in order to come up with these decisions, we need to conduct this sensitivity analysis. And when we are conducting global sensitivity analysis, most of the time you need thousands of simulations, right? But due to this object-oriented structure, we can do this quite simply. And we did this for different models. So we picked the Wu-Waldron fiber bundle model, the basic fiber bundle family, and the Waldron model. And then we defined ranges that we found from the literature for all the parameters, such as diameter, tensile strength, number of roots, load sharing factors, etc., etc., etc. Look at the variation of the results, right? So we created random samples. If I recall, that's around 5,000 samples for each model. So think like you have 5,000 soils with different number of roots of different diameters and different strengths and etc. So out of these 5,000, if you go with the fiber bundle and Wu-Waldron type model, you can get, even though they are statistically outliers, you can get values as high as 100 kilopascal, which is not realistic at all. We all know that there is not going to be 100 kilopascal reinforcement coming from the roots in the soil. And if you look at the Waldron model, which is actually the first model that was introduced, but that used the mobilization of the soil displacements, that has a much limited range, and in my experience, I could say a much more realistic range that we can obtain. And then afterwards, we can look at the effects, right? So we then take the root area ratio, which is defining the contribution of roots to the cross-sectional area of the soil, and that gives us the total reinforcement value, right, if we sum them up. And different models have different effects for that, right? So we see that for the Waldron model, we are actually getting a nonlinear effect if we consider also the interface strength here. And if we look at the first two models where there's no displacement involvement at all, we just have a very simple linear effect. And then we looked at what if we measured the root diameters wrong, right? If we measured, for example, the root diameters with an error of 20%, and my root area ratio now is estimated with a 20% error. And we see that for some models, the errors that were coming as let's say as 20% is now propagated as high as 50%. So when you make a wrong estimation of the root diameter, different models propagate this error differently, and you end up with different range of values. And in the Waldron case, this is actually not so high, the error propagation here, right? So this is just one example of what you can do by using this package or this methodology to test the effects of different hypotheses and to understand what is the uncertainty in my model and where it is coming from. So to sum up, with Pyrote Memo, you can easily and systematically compare many models. I mean, you have seen the implementation here basically in 28 lines of code. You can get 5 models and compare them very easily, and you can look at the peak reinforcement values, let's say within a few seconds. You can explore the effect of different model assumptions. You can run sensitivity analysis, and you can do many, many more things. So Pyrote Memo provides a transparent, free, standardized, reusable, and community-driven platform to advance the field of root reinforcement modeling. If you scan this QR code, you should end up with the project website and the repository. As I said, the code is publicly available. We are always looking for contributors. If you want to chat with me on this, I'm always happy to talk. We also have a contribution guidelines. And I didn't get into the software part of it. I'm just wrapping it up very quickly. I didn't get into the software part of it, but due to the implementation, we actually have designed a structure that is very easy to expand if you want to implement another model or if you want to implement another, let's say, model family or so. So with that, I would like to thank you for your attention.
Ok, great. Perfettamente in tempo, anzi un po' in anticipo, quindi grazie. Aspetta, facciamo un dono anche per te, grazie, da parte dell'ordine degli ingegneri della provincia autonoma di Bolzano. Grazie. Le domande le facciamo dopo il secondo intervento, intanto chiamo il prossimo speaker, Fabio ci aiuta a mettere il dottore Baldwin dell'Università di Dundee.
James Hutton Institute.
The James Hutton Institute di Dundee, no?
Yes.
Okay.
Before.
Ma italiano.
Yes.
Okay.
I will speak in English, but I'm happy to translate anything or to clarify anything in Italian.
Okay. I hope the video.
Yeah. Okay. Thank you.
Mi alzo 5 minuti prima che tu finisca. Ma...
Il laser pointer qui.
No, puoi usare questo.
Perfect. Thank you. Okay, so thank you very much. Thank you very much to the organizers for the invite. Oh. Okay, so it's okay? Can you hear me? Okay. So thank you very much to the organizers for the invite and the opportunity to present my research. I feel quite lucky because a lot of concepts have been already introduced.
Sorry, but we have a problem on the video. I don't know why, because salta sempre questa condivisione.
Nessun problema.
Tu hai questo. Ok. Ok, dovrebbe andare adesso, scusami.
No problem. So I was saying that I feel quite lucky because a lot of concepts have been already introduced, and in particular, a lot of issues, problems in this very transdisciplinary topic have been already mentioned, in particular by Manuela. Have been mentioned the importance to consider the biological nature of roots, the biological variability of these materials that now we are considering for their engineering function. So my presentation today will mainly highlight the effect of different species on engineering functions. So Anil has already mentioned that the two main processes that vegetation affect in terms of slope stabilization are mechanical and hydrological effects. So I will not spend the time on this. But if we look closer to vegetation, we can see that there are several engineering functions that can be affected by vegetation, several functions that are of interest for slope stabilization, as you can see listed here. In particular, in addition to hydrological reinforcement and root mechanical reinforcement, we have effects on infiltration. So vegetation does not only affect the removal of water from the soil, but also affect how water entering the soil and how fast move down a soil profile. Then have been already mentioned by Anil that vegetation can also affect soil structure and structural stability. And so I will now try to provide different examples how different species, different plant functional types and plant traits can affect these different functions, these different ecosystem services. Because if we want to replace traditional hard engineering techniques with vegetation, or if we want to integrate vegetation in this also traditional techniques, we really need to quantify the different properties of different species as much as we know the different properties of the different materials in traditional engineering. So I will start with hydrological reinforcement. So the reinforcement provided by soil drying induced by plant transpiration. And in particular, I will present a series of studies that move from laboratory and glasshouse control environment to the validation of these results in a field experiment. So we move through different levels of complexity. We have an increase of complexity through different experiments. It has been what have been discussed after the first two presentations. So how we move from control environments that can provide information about fundamental mechanisms, but often they don't represent what is happening in the field. And on the other end, too often we have field monitoring that are based on slopes that have been there for sometimes hundreds of years, stables on mature vegetations. So how we link these two different approaches, what happened in control environment and what happened in the field. And so for this reason, we have this series of experiments. So we started in a glasshouse control environment where we grew 10 woody species in pots with the same soil density. We have both deciduous and evergreen species. And we select these species because these are generally used in eco-engineering solutions, in particular for road embankment revegetation. So after the initial establishment of the plants in the glasshouse, in the pots, we saturated the soil in all the pots and we left them for evapotranspiration for a period. And after this period, we measured the hydrological reinforcement induced by the plants, that is represented by the relation between soil matrix action, so the drying of the soil by the plants, and soil strength that have been measured as penetration resistance. And you can see immediately that there are large differences between the different species, indicated here by their acronyms, and a clear effect in particular compared to the control unvegetated soil. So the different species largely differ in their ability to induce hydrological reinforcement. Now, the question is, can we use plant characteristics, plant functional traits to understand these differences. And so can we use these traits to then select the species to provide high hydrological reinforcement on a slope? So for this reason, we quantify 11 plant traits, 11 characteristics, both above ground and below ground characteristics for each of the 10 woody species that we tested for hydrological reinforcement. Right. Then we use some statistical tools, in particular principal component analysis, to identify what were the plant characteristics, the traits that were mostly associated with induced hydrological reinforcement, again represented by the change of matrix suction and penetration resistance in the soil. And we found in particular that the root length density, so the length of roots per volume of soil, the root shoot ratio, and the ratio between below ground and above ground biomass, and the specific leaf area, the leaf area on leaf mass, were the traits that were mostly associated with a change of hydrological reinforcement in our glasshouse experiment. Here you can see this in the detail, where you can see the relation between root shoot ratio, measuring the different species, with hydrological reinforcement, again indicated by matrix suction and penetration resistance. This is so for a sort of a below ground trait, but also we saw this for above ground traits. And here you can see a relation between the specific leaf area with hydrological reinforcement again. So from this study, we can say that different species largely differ in their ability to induce hydrological reinforcement, and also we can identify some plant characteristics, some plant traits that then we can use to screen a species to provide hydrological reinforcement on a slope. But at this point, we still don't know how the different species affect hydrological reinforcement down a soil profile, so looking at the soil depth, and in particular during different seasons. And for this reason, we selected 3 contrasting species from the previous experiment. We have Deciduous, Corylus avellana, 2 contrasting evergreens from the previous experiment, Ilex aquifolium, Ulex europaeus. And now we group them in soil columns, 1 meter soil columns, so we can look what happened down the soil profile, looking at the effect in soil depth. And we tested these species during summer and winter. So during summer and winter conditions for Scotland, again, we are in a glasshouse environment where we are able to control and mimic the condition of summer and winter. And these were mainly different, of course, in terms of temperature and relative humidity in the glasshouse environment. So, like in the previous experiment, after the initial establishment of the plants in the soil columns, we saturated the soil in all the soil columns for both the summer and the winter monitoring. And after the initial saturation, we started to monitor the change of matrix suction down the soil profile at 0.1, 0.3, and 0.7 meters, as you can see here. And you can immediately see the large differences between the species, because in the top soil, all 3 species were able to induce high value of matrix suction up to 70 kPa, while if we move deep in the soil at 0.3 meters, only 2 species now are able to induce the high value of matrix suction, and deeper again in the soil at 0.7 meters, only 1 of the species, only Ulex europaeus, 1 of the 2 evergreens, was able to induce high value of matrix suction. Then, if we move to the winter monitoring, similar situation, we saturate the soil at the beginning and we start to measure the change of matrix suction. Immediately you can see that the Deciduous was able to induce no change in the soil, this was expected, but also we have large differences in the 2 evergreens, with 1 still able to induce high value of matrix suction, but after a much longer period, 3 times longer period, and the other just a small value of matrix suction. If we look deeper in the soil, almost, let's say, no effect, a very small effect in a deeper soil layer. At the end of both monitoring period, we simulate a heavy rain event to look to the residual matrix action. And you can see that while in the topsoil layer we dissipate all the matrix action, in the deeper soil layers we were still able to maintain some matrix action. But of course we are not interested just to the change of soil hydrology. We want to see if this translates in a measurable change in soil strength. And so we look at the hydrological enforcement as soil strength gain in relation to matrix action in our soil columns during both summer, you can see the closed symbols, and winter, the open symbols in the graph. And in the control soil columns, where we have no plants, no change of soil strength during the entire monitoring period. Then if we look to the deciduous Corylus avellana, we can see that we have a clear increase of soil strength in the relation of change of matrix action in the summer period, but no effect during the winter period. Even we move to the evergreens, still quite contrasting data, still quite a strong species effect, because just one of the species was able to induce high value of soil strength induced by the change of matrix action down the entire soil profile during both the summer and the winter. So a clear species effect down the soil profile and during the different seasons. So the results that I presented up to this point were based on a glasshouse control environment. So there was the need then to move on field condition under climate and soil variability. So for this reason, we use the same three contrasting species to revegetate an embankment prone to failure. So where we revegetate the embankment with plots with different species. And we fully characterize the soil on the embankment, as you can see here. And then we started to monitor this embankment for 2 years for different physical properties, in particular for the change of matrix action along the embankment. Here you can see just 1 day of monitoring, just a representative day during the first growing season. And immediately you can see that there are clear peaks of matrix action in the plots vegetated with Ulex europaeus. That was also a species that was able to induce high value of matrix action and high value of soil strength in the previous experiments in the control environment. So we were able to transfer the information from the control environment to the field. And in less than 1 meter, you can see that we have a change of up to 70 kPa of matrix action. So a very strong species effect also in the field, also accounting for all the soil variability and the climate variability. We can still see these large species effects. But let's look now what happened in terms of soil strength. Here you can see the shear strength of the soil in the different plots. Again, just a representative day here during the summer. Clear peaks of soil strength, again in the plots vegetated with Ulex europaeus, same species that was providing high strength value in the glasshouse experiment. This during the summer, but then if we come back to the same plots during the autumn, we see that most of that strength now have been lost with dissipation of matrix action that you can see represented by the vertical bars on the bottom. So a quite clear seasonal effect in this case, and so we lost all the species difference during the autumn period. Another important and interesting effect of vegetation in terms of soil hydrology on a slope is the ability of vegetation to intercept rainwater. Anila has mentioned this. And here we were again interested to the effect of different species, different plant functional types, so the deciduous and the evergreens, how much rainfall these were able to intercept. This was again based on the revegetated slope. And you can see that in the case of deciduous, we have quite a large variability, in particular during the summer period, almost no effect during the winter period. So in some cases, we have almost a concentration of rain in some points, again due to the funneling effect of the canopy. If when we move to the two evergreens, again large differences also in terms of their ability to intercept the precipitation. Ilex aquifolium, very poor effect in terms of its ability to intercept a rain event, while if we look to Ulex europaeus, quite a large effect during both the summer monitoring and the winter monitoring, and also for relatively large and intense rain events. And this can help us to maintain matrix action that have been developed on a slope by transpiration. So we start in a control environment, we move through progressive complexity to the field, looking at the hydrological reinforcement, the reinforcement provided by different species. We found that Ulex europaeus, this evergreen, was the one that was able to induce the highest level of hydrological reinforcement. Can we further generalize this? And to do this, we came back to the lab. We look at physical modeling, where we reproduce embankments in scale, and we tested them in a geotechnical centrifuge, where we spin our physical model with and without vegetation, and at the same time, we induce some intense rain events. And we look to the movements of the soil on the slope, the destabilization of the slope in relation to the rain event. And we have also different soil density. And immediately you can see that this is the control soil, so no vegetation. And you can see that we have a large horizontal movements, but also vertical movements. While in the case of a vegetated slope, we have almost no deformation, no movement. So we can further generalize the effect of vegetation through this physical modeling in the geotechnical centrifuge. So now we will move to the effect on infiltration. So as I say, plants can also affect how water moves down the soil. Also in this case, I was interested to the effect of different species. But first of all, the question is, does vegetation affect infiltration and hydraulic conductivity? And the answer is yes, it's affecting infiltration, it's increasing infiltration. For example, in this experiment based on different species, we have in general a 4 times increase of hydraulic conductivity in the vegetated soil compared to the control and vegetated soil, but also we have large differences between the different species, as you can see here. And have been already mentioned by Manuela, this is a very dynamic system, the relation between soil and vegetation. And we found that we have an increase of the ability of soil to infiltrate the water with the aging of the plants for both herbaceous species and woody species. Not only an effect during the life cycle of a plant, but plants can in particular affect hydraulic conductivity and so the ability of soil to infiltrate the water after the death of a plant and the decomposition of the roots, when we have a creation of large root channels, especially for taproot system species. And here you can see the increase of infiltration represented by the blue bar, compare the initial measure before the decomposition of a root system. So you can see that there is an abrupt change of hydraulic conductivity and this down the soil profile. Again, a species effect. This is Daucus carota, a taproot system, while, for example, we have a Deschampsia cespitosa, a fibro-root system, so a clear difference. A question that we had at that point was, okay, water is moving very fast down the soil profile through this preferential flow domain. Does the water at that point get redistributed in the entire soil mass through the root channel? And to answer to this question, we need to know the physical properties of the walls of the root channel. So we look now at a much smaller scale. We look at just the physical properties of a soil in the root channel, and we compare these physical properties with the one of an unvegetated soil, with the one of a bulk soil. different species, also in this case, different plant functional types and the root system. And in general, we found that the soil in the root channel has a lower absorptivity, so a lower ability to absorb and transmit water. We found also that the soil in the root channel has greater hardness, so it's more compact, it's more dense than the surrounding soil. And for some species, after the decomposition of some species, in the root channel also we have high hydrophobicity. So we can see that this root channel acts like a pipe bringing down water, but has a poor ability to redistribute this water throughout the soil mass. Also in this case, we were interested if we can find some plant traits that can help us to identify species that can increase more than others the hydraulic conductivity in the soil, so can affect the ability of soil to infiltrate water. And so we looked to several plant traits, several plant characteristics, and then we found that the specific root length, so the relation between root length and root mass, was negatively related with the ability of plants to affect hydraulic conductivity, as you can see here. So in simple terms, as we move from taproot systems to fibro root systems, such as the one of grasses, we generally have a decrease of a plant ability to affect hydraulic conductivity. So now we can select the species to induce higher or lower effect on soil infiltration that can be of our interest. So I will now move to mechanical reinforcement, and the video that you can see on the screen show roots during a shear strength of the soil, and you can see how these roots mobilize their strength in different way. As have been mentioned, some roots will pull out, will just slip, some that you will see in the next slide, just a breaking failure. So we have a different mechanism. But in general, we found that for all the different species that we tested, from grasses to woody species, we have a clear increase of soil strength in the presence of roots when we compare to unvegetated soil. But this experiment, most of the time, are based on homogeneous soil column. But in reality, when we look to soil in a natural environment, this is quite complex. We have different layers, especially we have different horizons, especially when we look to soil in mountain areas. Generally are quite shallow, and we have a quite shallow bedrock. And so we look if vegetation can also affect the shear strength at the interface between these different layers, because generally a slope failure occur at the interface between the different layers where we have mechanical or hydrological discontinuity in the soil. So we have different soil columns. In the first example, here on the top, we have a soil columns just with soil, no different layers, and we look to the effect of vegetation. The black and green lines representing the vegetated soil. On the bottom red line is the control soil, and you can see that vegetation is providing a clear reinforcement, but still we have a good value of soil strength in the control soil. So let's now focus on the control soil. Let's see what happened when we have different layers. We have a top layer with a sandy loam soil and a bottom layer with coarse gravelly material. Very simple situation, much more simple compared to what we have in a natural soil. But so let's see what happened, and you can see that in the control soil, no vegetation, we have a clear drop of soil strength when we shear this soil at the interface between these two layers. But if we have a vegetation, if we have a plants, these are different species with fibrous or taproot system, in the soil columns, we can see that we are still able to maintain a similar situation compared to the homogeneous soil column. So vegetation is also able to provide a significant reinforcement where we have a soil with different layers and a clear weak shear plane between different potential horizons. So up to now I presented all the benefits of vegetation, but what happened when we clear vegetation? And this has been already mentioned, that we can lose a part of these benefits when we remove vegetation. It has been mentioned by Manuela, but also in the introduction by Anil. And generally we can remove vegetation using different methods, such as, for example, we can burn vegetation, or we can use herbicide. And we are particularly interested to these two different methods to remove vegetation, because this was a part of a collaboration with a researcher in Thailand, where the expansion of agriculture and other land use on marginal land imply the clearance of vegetation generally by burning or the application of herbicide. So the question was, does it change the effect on root mechanical reinforcement if we use one technique or the other to remove vegetation? How fast is the loss of this mechanical reinforcement? And so we have again, we work in this case in a control environment, in soil columns, where we have herbaceous species, and then we burn the vegetation or we apply herbicide. And we look, first of all, the change of root biomechanical properties. Here you can see tensile strength. And you can see that in the case of burning, the black vertical bars, you have an initial increase of tensile strength after the burning, and then a slow decrease. While if we apply herbicide on vegetation, we have a quick loss in less than 2 months. Less than 2 months, we have an important drop of root tensile strength with application of herbicide. So two very different mechanisms of loss of root biomechanical properties. And these were explained by the different dynamics in the composition of root tissues after the burning or the application of herbicide. As you can see here, for example, in the case of the burning, we have a slow decrease and a linear and slow decrease of cellulose content, which is the main structural polymer in the root tissues. While in the case of application of herbicide, we have a quick drop of the cellulose concentration in the roots. So a very different mechanism, also very different action on the plant biology. Now the question is, but does this really affect the reinforcement in the soil? We saw that this can affect the biomechanical properties, but let's look now what happened in terms of soil reinforcement. So on the top, you have the control situation, the original situation where you have a control soil, the continuous line, and then on the top you can see the vegetated soil that is stronger than the control soil in the relation between displacement and shear stress. Then, if we come back after the burning, after 2 months, we can still see that the soil, the vegetated soil is stronger than the control soil. So a clear effect, we are able to maintain this. But in the case of application of herbicide, in only 2 months, the now vegetated soil is weaker than the control unvegetated soil. If we go back then in the soil after the burning, we can see that after 12 months, also in this case, the soil strength dropped below the one of a control. So also in this case, what was vegetated soil, now it's weaker than the original control soil. So, very quick, last effect of vegetation, change of soil structure. Also, this have been mentioned before. So, I'm interested in particular to the effect on structural stability and the resilience of structure. So, have been mentioned of effect on aggregate stability. Here it's just another example where we grow different species in soil that has no structure, that you can see in the control. This was the control soil, the original soil. This is what happened when you introduce vegetation in that soil. This just after a few months. So in a few months, we move from a soil that we have a stability, aggregate stability percentage around 5-6% up to 35-40%. This in just a few months. This is the effect on soil structure, not effect on mechanical reinforcement, not effect of hydraulic reinforcement, just a change in the soil structure induced by vegetation. How much is the resilience of this soil structure to when a stress, a mechanical stress? We're interested to this. So we sample vegetation and we sample soil under different vegetation types from so same soil but different vegetation cover, woody vegetation, perennial herbaceous vegetation, and an arable field. And we take the soil in the lab, we sieve all the soil, and we equilibrate the soil at the same water potential. So again, no mechanical, no hydrological reinforcement. But you can see when we subject this soil to different loadings, so to different mechanical stress, and we look to the elasticity of the soil, how the soil responding to the mechanical stress, how the soil rebound when after the application of the mechanical stress, you can see that there are still large differences between the different vegetation types, despite we have sieve all the soil and we equilibrate all the soil to the same matrix action. And we are able to solve this for different level of stress that you can see here. So a clear effect on the resilience of soil to stress. So sorry, it took more time. So thank you for your attention.
Grazie. Precisissimo con i tempi, questo per te. Grazie ancora. Allora, abbiamo finito la sessione mattutina. Prima di andare a pranzo direi di fare, se ci sono domande o commenti sia ai due ultimi interventi che abbiamo sentito, sia ai precedenti due, se qualcuno ha fatto delle riflessioni durante il coffee break. Questo, Fabio, siamo collegati anche, possono parlare eventualmente in chat. Perché qui non riesco a capire il tedesco. Sì, non sono perfetto, lo so. Ma neanche Fabio.
Sabrina, noi nella chat non lo vediamo.
Intanto se dalla sala c'è qualcuno, inviati. Io poi ho qualche riflessione che volevo fare.
Intanto parla tu.
Però la faccio?
Sì.
No, ma semplicemente sono a considerazione, mi è venuto ascoltando questi studi che sono veramente interessanti. Volevo, dal punto di vista delle applicazioni, avere un po' il polso, essere sicuro di aver capito bene, fatemi dire così. Qualcuno ha detto, credo stiamo parlando di scorrimenti poco profondi, scorrimenti superficiali. Quanto superficiali? Questa è la prima domanda. Stiamo parlando di 1-2 metri o stiamo parlando anche di scorrimenti fino a 8 metri? Perché tradizionalmente frane superficiali, perlomeno da evangelista, erano classificate fino a scorrimenti di circa 8 metri, no? Stiamo parlando di quel range di profondità o stiamo parlando di profondità inferiori? Questo, diciamo, dopodiché giustamente in tutti i modelli si parla, diciamo, l'effetto della radice viene quantificato in un momento della coesione efficace e, diciamo, è abbastanza ragionevole, perché perlomeno nei terreni saturi per scorrimenti superficiali il contributo attributivo è molto modesto, cioè il termine del criterio di resistenza di Colombo, primo N per tangenti φ per stati intenzionali modesti dà un contributo molto modesto, e quindi concentrarsi sulla coesione, cioè che la coesione abbia un contributo molto maggiore è giusto, insomma, mi torna. Anche qui, che lo possiamo quantificare questo incremento? Quanto pesa in termini? Perché io ho visto gli sviluppi a rottura rappresentato la professoressa Cecconi, e non ho fatto in tempo a capire, si raddoppia la coesione, il contributo è del 100%, 50%, cioè di quanto cresce la resistenza al taglio su queste colte superficiali. Quindi la prima domanda è quanto superficiale, la seconda è di quanto è l'incremento della resistenza. Questo giusto per inquadrare e dare anche, diciamo, a chi si occupa dell'applicazione, a dare un riferimento per capire, per me, collocarci in una casella giusta, no?
Io ti chiedo, stai riferendo all'effetto meccanico o anche quello idraulico?
No, all'effetto sulla stabilità.
Complessivo,
sì,
senz'altro, contemplando l'effetto idraulico, prescinde dalla profondità, cioè riesce a cambiare l'andamento della filtrazione, quindi valore delle pressioni interstiziali sino a significative profondità di dipendenza dai caratteri, dalle proprietà idrauliche dell'ammasso, perché stai riducendo il tasso di infiltrazione nel tempo, infiltrazione netta, quindi al netto anche dell'evapotraspirazione, quindi la mitigazione è anche per
a probabilità elevata.
Questo è molto importante, questa
certo.
valutazione. Per l'aspetto meccanico,
sì, per l'aspetto meccanico invece io ho fatto sempre riferimento a fenomeni superficiali, quindi 1 massimo 2 metri, perché è quello spessore che viene intercettato da apparati radicali che possono anche raggiungere profondità di quel genere. Quindi sì, facevo riferimento
a momenti superficiali. No, infatti io ho fatto la domanda proprio per questo, perché l'influenza della vegetazione e quindi delle pressioni in generale si sente a grandi profondità, come giustamente Federica ha messo in evidenza, e quindi però volevo che ci fosse questa distinzione cioè serve per entrambi, ok? Da una parte per quello domanda online, c'è una domanda della professoressa Cotecchia, vai.
Una domanda per Jerry Baldwin, un paio. Innanzitutto congratulazioni, bellissima presentazione. Il terreno, parlato di